So in terms of locating it, there's no surprises. We find the derivative. How many times can we do that? So we want to find the derivative of f dash of x, and again, we want to put f dash of x equal to 0, okay? That will give me the x values of the stationary points. What I then want to do is find the corresponding y value, and then that gives me the actual coordinate of my stationary point. The first derivative test is just testing either side of the x coordinate, okay, to see whether it's positive or negative. We don't really need the value. I just need to know if it's a positive gradient or a negative gradient. All right. So let's find a few stationary points and their nature. All right. So let's just get a bit more space. First things first, let's find f dash of x, and that's equal to 4x minus 3x squared, and I need to solve that equal to 0. So f dash of x is equal to 0, so that implies if I factorise that with an x out the front, I'll get 4 minus 3x is equal to 0. Therefore, x is equal to 0, or x is equal to, take the 4 across, divide by 3, I get positive 4/3. So they're the x coordinates, all right? So the corresponding y values, well, f of 0 is equal to 0, so that coordinate is 0, 0. F of 4/3 is equal to, what's that? 2 times 4/3 squared minus 4/3 cubed. Let's come in here, which is 2 times 4 on 3 squared is 16 on 9, minus 4 cubed is 64 over 27. So let's try and get it. So it's 32 on 9, make them both on 27. So 32 times 3 is 96 on 27, minus 64 on 27, which is 32 on 27. So that coordinate becomes 4/3 32 on 27. So what we need to do now is work out their nature. So let's consider at x equal to 0. So their nature, so what I've got, I guess there's a couple of ways we could consider this. I actually know I've got a cubic graph, and at x equal to 0 is a turning point. Where was the other one? At x equal to 4/3. So you can see from the graph, you'd expect the first one to be a minimum and the second one to be a maximum. So let's check. So if I work out, pick a value just left, say -1, okay? F dashed of -1 is equal to what? It's equal to 4 times -1 minus 3 times -1 squared, which is -4 minus 3, which is less than 0. Oops. Let's rub that. Less than 0. So the derivative, so therefore f dash of x is less than 0. So we've got a negative gradient at that point, which coincides. We know it's a 0 gradient at x equal to 0. So what we need to do is pick another value just to the right of that turning point. Now, given our other turning point is at 4/3, I need to pick a number less than 4/3. So if I pick f of 1, so if I pick f dashed at 1, my derivative is equal to 4 minus 3, which is greater than 0. Yeah. So I've got a positive, so I go a negative gradient, 0 gradient, positive gradient, therefore I have a minimum value there. If I want to check at 4/3, well, f of 4/3 is equal to 0. F of 1 I've already checked, and that's greater than 0. So I've got greater than 0, equal to 0. Pick a number greater than 4/3, say just 2, number that's easy to work with, and that's equal to 8, f dashed of 2 I should say, is 4 times 2 is 8, minus 3 times 4, which is 12, which is less than 0. Okay, so in other words then I've got a negative gradient, so therefore it's a maximum at that point. All right, so I know the stationary points. Oh, I I know my stationary points. My stationary points are at 4/3, 0, 0. And I now know which one's a maximum and which one's a minimum. All right, let's go again. 2x cubed minus 2x squared plus 4x minus 15. So we have to work out the derivative f dashed of x. And that's equal to 6x squared minus 4x plus 4. Now I've got to solve that equal to 0. So a little bit of factorising. So let's maybe take 2 out the front. 3x minus 2x plus 2. And I'm hoping that that will cross multiply well. 3x and x. And what are we going to do here? Positive 2, 1. That's not going to work. So what we might need to do now, let's consider our quadratic formula. So quick check. Let's factorise that thing. So let's do a b squared minus 4ac. So b squared is negative 2 squared minus 4 times a times c, which is 4 minus 24, which is less than 0, isn't it? So it's negative. So there's no solutions. So in this particular case, our derivative doesn't equal 0. So there are no stationary points. So let's have a look at what this graph will look like. We use a little bit of Desmos or something like that to graph this particular graph. We find that it actually looks a bit like that. So there's actually no turning points and no points of inflection in this case. So look, it's not something that we come across too often, but it just really highlights the fact that not every cubic graph is going to look like the traditional cubic. Okay, this one here happens to have no stationary points, and so that's roughly what it looks like. So let's go on to the next one. Y equals x squared e to the 2x. So let's move it all up a little bit. So let's have a look. So we've got a product rule here, haven't we? So u is equal to x squared, which means u dashed is equal to 2x. I'll put v equal e to the 2x, which means v dashed is equal to 2e to the 2x. So dy dx is equal to, we'll say derivative of the first, which we'll call 2x times the second, plus derivative of the second, which is 2e to the 2x times the first. So if I factorise that, what have I got common? I've got a 2 common, I've got an x common, and I've got an e to the 2x common. So that's a 1 here, and I reckon it's a plus x on the other side. Okay, so there's my derivative. So now I want to solve that equal to 0. So dy dx equals 0 if 2x e to the 2x is equal to 0, which implies x is equal to 0, or if 1 plus x is equal to 0, so x is equal to negative 1. So my coordinates are 0 something, negative 1 something. Corresponding y value, if I put 0 into that equation there, I get e to the 0 times 0, which is just 0. If I put negative 1 in there, I get negative 1 squared, which is 1. 1 times e to the minus 2, which is just e to the negative 2. So they're the actual coordinates of my turning points. So let's find their nature. Often it's good just to do a little table to help determine their nature. So let's just put a little f dashed of x there. So my stationary points are at 0, at x equal to 0, and at x equal to negative 1. So let's change that into a negative 1 there. A number in between, let's put a 0 there, and another number in between. Okay, so let's think about that. So let's pick, so if I pick negative 2 A number between 0 and -1, I might have to settle for -1/2, and a number bigger than 0 is just 1. So let's work out the derivative at -2. The derivative at -2 is 2 times -2 e to the 2 times -2, 1 minus 2. So 2 times -2, so that's a negative number. That there is a positive number. 1 minus 2 is a negative number. So I get negative times a negative, so it's a positive. So I get a positive gradient at -2. I've got a 0 gradient at -1. So what about -1/2? What's -1/2 give me? That'll give me 2 times -1/2 e to the 2 times -1/2 outside of 1 -1/2. 2 times -1/2, well, that's negative. That's positive there. 2 to the minus e to the -1. 1 -1/2 is also negative. So that gives me a positive value. Sorry, let's go back. 1 -1/2 is positive, isn't it? So that actually gives me a negative value. So that's okay. So at -1, -1/2, I should say, I'll get a negative gradient. So that makes that point there a maximum. At 0, we have a 0 gradient. At x equal to 1, what does f of 1 equal? F of 1 is equal to 2 times 1 e to the 2 times 1, 1 plus 1. So that's positive, that's positive, that's positive. So I get a positive gradient. So there we are there. So we can sort of summarize everything. So the point 0, 0 is a minimum, and the point -1 e to the -2 is a maximum.